Hi, this is Macie Watley, Lab M03. This is my Lab 3 Constant Velocity Motion Report. I made an observation of a rolling bowling ball in the Tech Rec in the Student Center, modeled it, and the main result, using Newton's second law, was assuming net force equals 0 allows me to predict the position of the bowling ball. Here's the video of a guy bowling a ball down the lane. It's the 10-pound ball in the Student Center. And I will play that for you. I used a clip after the ball has been released and before it hits the pens. I used an iPhone for recording, so the ball is a little blurry, which may have caused some error. I calibrated using the diameter of the bowling ball when I zoomed in, put it into meters, and I found that information using Wikipedia. And I set the origin at the center of the ball at the beginning of the clip, as you can see right there. And I used the center of the ball as the average position when I was tracking it. The time between frames was 1/30th of a second. I found the mass to be 4.536 kilograms for the bowling ball, and then used that information and the information from the tracker video to calculate the average velocity. As you can see here, which I did the final position minus the initial position divided by the final time minus the initial time, which came out to be 10.144 meters per second. And I updated the information to the program to fit my experiment. I changed the axes to be a little bit larger to show the ball, because my ball went off screen without changing that, but that's just a visual thing. The ball's mass is, I put that in here. I changed the velocity, and the start time is still at 0. I changed the time set, the delta t, to be 1/30 for the changing frames, 1/30 seconds. My whole time clip was 0.333 seconds, so I put that in there. And then everything else remained the same. Very important to note that the net force is 0. And assuming that the net force is 0, we should see a constant velocity. So this will be when I run this. It looks like this. As you can see, the ball started at 0 and rolled. So I put all of the data into spreadsheets. This is the data from the tracker video, which I just copied and pasted the T and the X columns there into the position versus time. You can see a very linear relationship. I got the regression line to see what the slope would be, which would be the velocity, and that's 10.156 meters per second. Very important to note that time is seconds and the position is in meters. I then took my model, and I also from Python, and I copied and pasted that into another Excel sheet, and here's that line, which is also very linear, and as you would expect, it's 10.144 for the slope, because that's what I told it to be when I changed the velocity in there. Here are the two, the data from Python and from Tracker plotted together. They are at the same time, since both were stepped by 1/30, and the data from Tracker is in blue diamonds, and the data from Python is green triangles, and they lay right over each other, showing a very good fit for this, which is exactly the result we wanted, because this shows that with the net force equal to 0, there is a constant velocity from the bowling ball. I had chosen a different point of origin. My position coordinates would have changed, but the change would have shifted. The change would have been the same for each of the points, so it would not have made a difference in the actual velocity. Yes, it is possible to figure out all the different forces. For example, the force of friction from the lane, air resistance, gravity, things like that are forces could be considered negligible, but nonetheless still there. It's possible to approximate all of these forces. On shell to be 325.0 to show that if F net is not 0, there will not be a constant velocity. And when we run this, you can see there's a change in speed and a change in direction. So the velocity is not constant. But with F net 0, as previously shown, the ball had a constant speed. like so. Just as we had predicted.